In this example, I'm going to do a simple harmonic motion kinematic example that's not from the book. A 0.80 kilogram object is attached to one end of the spring and the system is set into simple harmonic motion. We notice the displacement of the object as a function of position here in this graph below, and we're supposed to find a whole lot of things about it. The amplitude of the motion, the angular frequency, the spring constant, the speed of the object at 1 second, the magnitude of the object's acceleration at 1 second, and the maximum velocity of the object. All right, so go ahead and see how much of this you can do on your own. Start with doing some analysis and planning, and go through and see how much of the execution you can do. Whenever I see a question like this with a graph or even with the equation, the first thing I do is try to figure out everything I can from that. And for graphs and equations, the two easiest things to figure out are the period and the acceleration. So remember, the period is defined as a time for one complete cycle. So here that would be start, up, down, back to start, ready to do the up, down again, right? So here they've shown us only one cycle, and the time to complete it is 4 seconds. So that means I know that the period is 4 seconds. All right, amplitude is another thing that I can easily read off a graph, right? If we remember, the amplitude is the maximum displacement from equilibrium. All right, and if we look at the graph, we can see the maximum displacement is either the equilibrium is at 0, the maximum displacement is up here at 8 centimeters, or down here at minus 8 centimeters. So basically, what we imagine is we have a mass on a spring, here's its equilibrium point, and it's swinging back and forth, up to positive 8 centimeters and down to negative 8 centimeters. Maybe I'll even draw that. Right, so what it's doing is here it would be at equilibrium, and it's moving along, it would be oscillating back and forth between plus and minus 8 centimeters. All right, so that's actually part A for us right there. Amplitude is 0.080 meters. All right, next, so now I consider this to be the analysis, that I figured out the period and the amplitude. And in fact, part of my analysis now, I'm even going to write down the equation of this since I've figured out enough to do that, right? And once I have the period and the amplitude, the only thing I need to figure out is it a sine-like or cosine-like one? And here we can see this one looks like a sine, right? It starts at 0, goes up, down, and back to 0. And that's exactly what sine does. If this had been a cosine, it would have started at its maximum and then gone like this instead. Okay, so why don't you see if you can use the information we've written here to write down the equation for this motion? All right, when we write the equation, we want to remember that there's a generic form if we have a sine. It's the amplitude times sine of omega t, or you can also think of it as the amplitude times sine of 2 pi over the period times the time, right? And this is the equation that describes the motion here in this graph. And we just have to match up A to its value and the period to its value, which is what I did here. And then that's handy because 2 pi over t, or omega, the thing that comes in front of the t, this thing right here, is the angular frequency, which is what we are asked for in part B. So now I can just write that down. Here we go. Omega, our angular frequency, is 2 pi over the period, or 2 pi over 4 seconds. So when I plug that in, I get 1.57. Remember, this 2 pi has a unit of radians with it, and omega should be in units of radians per second. So this gives us a radians, and this gives us a seconds, and we end up with 1.57 radians per second. All right, let's move on to part C, the spring constant. See if you can figure out how to do that one. Well, here my plan is going to be to use this equation that relates the period, the mass, and the spring constant. And since I know the period and the mass, it's pretty easy to find the spring constant. Just some algebra. Go ahead and do it yourself. All right, here I'm just doing the algebra. I start with this equation. Divided by 2 pi. Then I squared both sides to get rid of this square root. That means the 2 pi, the whole thing gets squared, so I put the parentheses there. Then I just, from there, solved for k, plugged in my numbers, and got 1.97 newtons per meter. And then I realized I hadn't been being careful about significant figures, because if we look at this graph, the positions and the masses here and the displacements here have 2 significant figures, 3 and 2 significant figures, and the time has 2 significant figures. So I really just need to have 2 significant figures, which I did here, but I hadn't been careful about up here, so when I was careful, I get 1.6 radians per second with the 2 significant figures. All right, so now I've got K, I've got omega, I've got the amplitude. Next, I want the speed of the object at the time equals 1 second. All right, so I wrote my goal here. And this I can get in a couple of different ways. One way would be to use the equation, and I could remember that if this is the general equation for x, then when I write the velocity, what happens is the sine turns into the cosine and I get an omega out front, and then I could plug in the time of 1 second to do that. So feel free to do that if you want, but I think it's easier to get it from the graph and from thinking about the story. So the story is I start at 0, but I have some velocity, so then I go out to my maximum and oscillate back and forth. And here, when I look at my graph at 1 second, I'm up at the maximum. So that's the maximum spring extension. And I know that for a brief moment at the maximum and minimum spring extension and compression right here and right here, that the mass is briefly paused before the spring pulls it and it heads back here, right? So as it's oscillating back and forth, its velocity is briefly 0 here, and in the middle it's actually the fastest. We can think about that from an energy perspective too, because here when the spring's not compressed, all the energy is kinetic, but when it extends out to the maximum, then it doesn't have kinetic anymore, and all the energy is in the potential energy of the spring being stretched. Okay, I can see that from the graph here too, because if I look at the slopes, right up here at the top and the bottom, the slope is briefly 0 because it's flat for a moment. So that means the velocity at t equals 1 second is 0. All right, so that means the next place we want to go is the magnitude of the object's acceleration at the 1 second time. So see if you can do this again. You can either use an equation, the graph, or tell yourself the story of the math. See if you can use one or all three of those to get out the get out the acceleration at the time equals 1 second. All right. So if I want to find the acceleration at time equals 1 second, my plan is to use the fact that since I know the force is minus kx, and force is mass times acceleration, this is something we saw in class, that acceleration is proportional to the opposite of the displacement. So if the displacement's positive, the acceleration is negative, and vice versa. So I'm going to use that to easily make a graph like this of x versus time, but for acceleration versus time. See if you can pause here and make that graph yourself. I start by realizing that if a is proportional to minus x, if x is 0, a is 0. So here, at 0, 2, and 4 seconds, a is going to be 0 here. So I put little dots here to remind me that it's 0. And then I know if x is big and positive, that the acceleration is big, and so I put a dot down here for that. And if the acceleration is big, if the position is big and negative, that means the acceleration is big and positive. So I put a dot here for that. And then if I just connect them and give it the same shape as x, but the negative, I see that it looks a lot like a sign, but a negative sign, curvy like that. And then if I look at the 1 second time, what I see is acceleration has its maximum value, but negative. And that's because displacement has its maximum value, and positive. Okay, so acceleration has its maximum value, but it's negative. Does that make sense with my story? So here's a spring oscillating back and forth. At 1 second, it's over here at 8 centimeters, its maximum extension. And that makes sense that it would be then accelerating in the negative direction to the left, because the spring would be pulling it to the left. And also the spring force would be the maximum here, so it makes sense that it would feel its maximum acceleration. Now that we know that the acceleration has its maximum magnitude, that we know how to calculate. See if you can remember how to calculate it and do that here. So this is something that you will see from your notes, that the maximum acceleration is the amplitude times the angular velocity omega squared. And so we can just use this equation, plug in the numbers here. Notice how I kept these with extra sig figs because I knew we were going to use them as an intermediate for later things. When I plug that in, I get 0.197 meters per second squared, or 0.2 meters per second squared with the correct sig figs. And just notice, remember, as before in angular motion, I ended up with meters times radians per second squared, but the radian is just a placeholder in that context, and I end up with meters per second squared. So our next goal is F, the maximum velocity. And if you look, there's actually an equation quite similar to this one for maximum velocity. Why don't you try to use that and find the velocity now? So it looks very similar, except the maximum velocity is a times omega, 0.12, which when I plug in everything gives me 0.12 meters per second. Then I realized that I forgot to include my negative sign in here. This one, because it's going to the left, should be 0.12 meters per second, but negative. All right, so it looks like we finished here. I just want to do a little monitoring on this one, make sure it makes sense the way I have on the others. So the maximum velocity is 0.12 meters per second. When would that happen? So when I'm oscillating back and forth, my maximum velocity actually happens in this middle point, right, as I'm quickly zooming through the equilibrium. And when I look here, I see that that would happen right here, or maybe right here and here, as we pass through the middle. Indeed, those do have the steepest slope of anywhere on the graph. All right, so I think I'm done with using a graph and the kinematics equations to think about simple harmonic motion.